Okay, so where were we? So after that, we're going to get into the whole issue of what do we do when you've got multiple chiral carbons in the same compound, which you can certainly do. And we'll talk about that later. And I'd like to get as far today as drawing the little structures that actually are what we'll later learn are Fisher projections in disguise. And I'm assuming you saw this in the reading. You know, you've got these things that look like this and have wedge bonds on the sides, right? And then going vertically, you've got only straight lines and dotted bonds. I didn't have it, I got in kind of, well, I was in this room, I was quite early, but I was not on campus early enough to go to my office and get my molecular modeling kit. I'll certainly have to bring that on Wednesday. But I'm assuming you read about these in your reading. Later on, we're going to learn, later on, by which I mean next term, we'll learn that there's even a further shortcut than this. You can use Fisher projections, which are not to be confused with Newman projections. They're a different critter. I'd like to just, I hope we get as far today as at least as introducing this idea. And I always get a few students that ask about this because yours is the very first organic textbook, and I've used probably 6 or 8 of them over the years. Yours is the very first that doesn't actually introduce Fisher projections in this chapter, so congratulations. So there's always some students who, when we get through this material, are asking me, look, Dr. Waz, is it okay if we use Fisher projections? And I love it. I love the initiative. I love the curiosity, but I'm going to have to say no, because since the book puts that off till later, I want to take advantage of that and save opening that whole can of worms until later. So when we get to that point, and like I said, I hope to get there by the end of today's lecture. When we get to that point, or until we get to that point, we'll just learn that this is another correct way of drawing structures with multiple chiral carbons in them. And I fear I'm going to have to save proving to you that this is an okay way to draw structures until Wednesday, until next time, because I don't have my molecular models with me. But I'm hoping, like I said, that we at least get that far. And then we'll get into the whole wonderful area of enantiomers versus diastereomers, which are also called diastereoisomers, just in case the first word wasn't quite long enough for you. And we'll learn about one of the strangest creatures we've learned about to date, the meso compound. That will be Wednesday. So we'll get to that later. Good, so that's kind of my game plan for today. If we can get that far, I'm pretty happy. Where are we at? 5 minutes to 11. Good, we have 35 minutes. That should be enough time to take care of all of this. Any questions then before we dive into that? Have I missed anything important? The room falls silent. Okay, so as I said, here's our 2 enantiomers of 2-butanol. And again, we can be confident that these are enantiomers and not the other thing, diastereomers, because there's only one chiral carbon. And I've tried to make it as clear as I can that those are mirror images of one another. And if you tried to make molecular models of those and cram them on each other to see if you can get all the corresponding atoms to superimpose or fall on one another, you would find it's not possible. You'll always have 2 groups that don't match, no matter what you do. And so those are enantiomers. They are mirror images of one another. And so as I said, one of those is the R enantiomer and one of those is the S enantiomer. And by the way, I don't know which is which right now as I stand in front of you. So that tells you something. I have not memorized it. However, I have a method that I know will work, and I trust it. And I think you can trust it too. And I've given you guys that method in the class notes. I've tried to make it as step-by-step as possible. In the class notes for section, that must be 5.5. Let me just double check. 5.5, yep. So maybe I'll write that over here, 5.5. So you can find all that in the class notes. I've given you all that. Let's then learn how to apply it. What the rule says is that we're going to assign all 4 of the groups on the chiral carbon a priority from 1 to 4. Not unlike, oh no, I'm getting confused. We haven't done alkenes yet, and cis and trans versus E and Z. That actually comes later. We flipped that around for some reason in 222. So that meaning that for you guys that it's something that's going to come in handy later on too when we talk more about alkene stereochemistry. But be that as it may, we're going to assign all 4 of those groups a priority from 1 to 4. And the rules state that you need to be looking at the structure in one of these ways such that the group of lowest priority, which will often be a hydrogen, not always, we'll hopefully do an example where there is no hydrogen. There still will be a lowest priority group. And I'll also let you know right now that priority is decided by atomic number. At least that's the official way. So you can see why hydrogen's going to be 4th priority. Its atomic number is 1, right? It's element number 1. So that's going to be the lowest one, but it's decided by atomic number. And so I think you can see here the remaining 3 groups. We've got 2 carbon groups, and we've got an oxygen. Well, oxygen is the highest atomic number of all of these. Right, oxygen is element number 8. And so that's going to be priority 1. The oxygen's going to win. And the hydrogen's going to be priority 4. Now, what about these 2? Well, these are both carbon atoms here. And so in cases like that, we need to go out another atom. And you'll eventually find something that breaks the tie. I had a colleague at my previous school who compared this to playing a game of war. I don't know if people still play that card game nowadays. But it's been, 1,000 years since I've played it. But as I recall, you put out your card and your opponent puts out their card, and it might be a tie, in which case you do it again. And you keep going until one of you wins. Well, same thing here. So we'll go out one more bond from that carbon. I see only hydrogens bonded to this carbon. However, one of those bonds from this carbon is bonded to another carbon. And that carbon beats the hydrogen on the methyl group. See what I mean? It's element 6 as opposed to element 1. And again, all this is in the class notes. But if at first you've got a tie like we do here, then you just keep going out until you break the tie. Or if it's a ring, you keep going around the ring until you break the tie. At this point, students become concerned, what if we get a trick question where you never break the tie? Do you see the concern? That's something I hear students being concerned about at this point. And I understand it, but I'm also here to tell you you don't need to worry about that. Because if you keep going all the way out to the end or all the way around the ring and never break the tie, what does that mean? That means the carbon atom has 2 groups that are the same, and therefore it's not chiral. See what I mean? Does that make sense? So you don't have to worry about that. That's not a concern. If you actually go all the way around or all the way to the end and never break the tie, the carbon's not chiral in the first place. So we'll only be seeing situations, at least when we're assigning RNS, where in fact we do break the tie eventually. And here we do. So does everyone see what I mean by that? That we have a carbon on this methyl group that beats all the 3 H's. Carbon beats hydrogen. Carbon's element number 6, hydrogen's element number 1. So that tells me that the ethyl group is of 2nd priority and the methyl of 3rd priority. So far, so good? We'll do the same on this one. The oxygen's going to win. Ethyl is number 2, methyl is number 3, and hydrogen is priority 4. Like I said, we'll deal with situations where the lowest priority group is not in the front. We'll learn how to deal with that. That's a 4, though. You'd be hard-pressed to know it. And can we determine priority by atomic weight as well? Excellent question. I think you mean atomic weight. Excellent question. Does everyone see the question in chat? Can we do it by atomic weight as well? In the answer technically is no. Officially, it's done by atomic number. But practically, I think you can see it'll work out the same if you use atomic weight. So it's just that the official rules state that you do it by atomic number. Yes, there are a couple places in the periodic table where there's an inversion. You've got an element with a higher atomic number than the previous one, but a lower atomic mass than the previous one. So that does happen 2 or 3 times in the periodic table. But they're like transition metals. You know, we're not ever going to see bonds to them. So it's a good question. The answer is technically no, but in real life, it doesn't matter. You can do it that way too. But the original official rules say you use atomic number. No, it's a good question because it's very easy to wonder, why is he emphasizing atomic number? Only because that's what the rules say. For whatever reason, that's how it was set up from the beginning. Good. So we've got our priorities going. And again, you also need to make sure that the lowest priority atom is facing back, is on a dotted bond. We'll deal with what happens when it's not. I'll show you some methods to deal with that. We've got a few of them. But here we have it pointing in the back. And then what you're going to do is, and you can use any of a variety of visual aids to help yourself to do this. You're going to imagine it like turning the wheel, a steering wheel or the funny wheel on a boat or whatever it is, you know. And you're going to go from 1 to 2, 2 to 3, 3 back to 1, and ignore the 4. I've learned over the years this is the absolutely clearest way I can think of to state this. And again, all that's in the class notes. You turn from 1 to 2, 2 to 3, 3 back to 1, and you ignore the 4. Just go right through it, wherever it might be. Just don't even think about it. So we're going to go from 1 to 2. You know what? Let me use another color. Yes. Exciting. So we'll go from 1 to 2, 2 to 3, and 3 back to 1. We'll ignore the 4. And then you simply observe whether that's a left turn or a right turn. Or you can think of it as counterclockwise or clockwise, respectively. You can use either left or right turn or counterclockwise or clockwise, whichever is easier for you. Either way, I think you'll agree that's a left turn. I mean, I'm not driving I need to be driving my car in the same direction as you guys, right? So it's a left turn. And if it's a left turn, then you assign it the absolute configuration S. We do use atomic weight if there are isotopes, though. Oh, that's a good point, if there are isotopes. Yes, so if it's a tie-in atomic number, but not an atomic weight, then you go to atomic weight. We'll do an example like that, so that you can see what we mean by that. The most common isotope you're going to come up with, I think, is deuterium. Deuterium is hydrogen 2. So yes, deuterium would beat normal hydrogen. We'll do one like that. Anyway, since this is a left turn or counterclockwise, this one we'll call S2-butanol. And then, of course, by process of elimination, that one must be R2-butanol. Let's verify that. So we're going to go from 1 to 2, 2 to 3, 3 back to 1, and we ignore the 4. Just go right through it. And that one is a right turn or clockwise. That one will be our R2-butanol. And I should mention, I don't even know which of these two is plus and which of these two is minus. There's no necessary connection between RS and plus minus. It's known somewhere. You could look it up somewhere. But there's no necessary connection. S might be plus and it might be minus. R might be plus and it might be minus. And another compound, it could be the opposite. So I do want to make that clear. There's no connection between plus minus and RS. And so basically what we've done is now if we need to know whether it's plus or minus, then we look it up. But otherwise, if we need to classify or name a compound, we use R and S, because all we need to do is examine the structure. It's independent of any other thing. So that's why they developed this system. And as such, it's very powerful. So yeah, I need to remember to do, okay, so let me get one set up over here that has a deuterium in it. Or you could do one with oxygen 16 and oxygen 18. You know, it's the same idea. What are we going to do then? Let's save that until later. I'll be a meanie. And I'll even put the methoxine back. So what if you're not given a case where the lowest priority group is already in the back? Oh, question first, yes. Where did the 2 come from? The 2 came because, well, one of the, oh, did I hear you right? Oh, yeah, the 2 came because both of these are carbon. So one is to be 2 and one is to be 3. The oxygen's going to beat that because oxygen is element number 8, carbon's element number 6. So the question is, we need to break the tie between these two since they're both carbon. And the way you do that is you go out another bond. And eventually on this one, you'll see we've got a carbon-carbon bond here that we don't have over here. This one's just bonded to hydrogen. So this carbon will beat that hydrogen. Even though those two carbons are a tie, when we go out another bond, this group wins. And that will always work, and there are no exceptions, and you can trust that method. It's like I said, if you keep going and keep going, either along a chain or around a ring, and you never ever are able to make a determination that it's just always and always a tie, well then the carbon's not chiral in the first place. You've got two groups that are the same. So you don't need to worry about that happening. Did that answer your question? Good, just wanted to make sure. Good. Why does it beat it? Do you just add the atomic numbers? Oh, okay, well, let me draw this out a little bit then. I'll just draw part of that molecule. And I'll leave this as a CH3. So will you agree I've transplanted part of that molecule over there? Is everyone clear on that? So the problem is that this carbon and this carbon are the same. It's a tie. So we need to go out a bond in order to make the determination. This carbon is bonded only to hydrogens. This carbon is also bonded to two hydrogens. That's still a tie. But there's also another carbon attached to that carbon over here. And this carbon beats that hydrogen that it's matched with. Does that help in chat also? A quick answer to the first question, do you just add the atomic numbers? One word answer is no. You don't add the atomic numbers. So you see that these two green things are a tie. When that happens, you go out another bond from where you were at. And if these, if there were another carbon on this one, you'd keep going out another bond. I mean, I don't think we're going to have time to do an example of every single possible permutation you can come up with. I'm going to let you, so the carbons don't matter, it's just about having more bonds. Well, the carbons do matter in the sense that one of those carbons eventually is going to beat this hydrogen. So these are good questions. This is probably one of the harder parts of this chapter, is being able to apply the Cahn-Ingold-Prelog rules. And I can't do an example of every single possible permutation, but I can at least give you the tools to use to go figure out that kind of thing, right? So it could essentially be any atom, right? If this were a chlorine, same thing. You would have the same priority, CH2Cl versus CH2CH3, or if it were CH2OH, that would come up with the same possibility. So we'll do more examples, but I think that will clarify that for now. So yeah, you're going to have to practice this, but yeah, you're going to be able to break that tie eventually by definition if the carbon is chiral. That's basically what I think you'll find with some practice. Good. So so what if owl is evil, or what if I even am evil, and I don't give the structure to you in the most efficient, straightforward way? What if you get a structure where, well, here you go. Let's look at this one. What if you get a structure where the lowest priority group is not pointing towards the back? By the way, have you noticed what I'm now featuring? Notice I'm not putting the lone pairs in the oxygen. Congratulations, you've graduated past the first exam. You don't have to put them, unless you need them to communicate something, right? If you're drawing a mechanism and pushing arrows and you need to show those electrons, then of course you should. Other than that, I hope we're familiar enough with structures by now that those lone pairs are understood. We understand oxygenobase, the octet rule, and there's two lone pairs there. I would say certainly if you're looking at an atom with a zero formal charge, we often drop them. Actually, I'm pretty sure, haven't you guys noticed in OWL, they often do that too. Now, if this were CH2O minus, then I'd put in the lone pairs, I think, so that you can see that it's got one bond and three lone pairs. So congratulations for getting past the first exam, but I do want to be picky about that at first. After that, we relax that a little bit, as long as the structure is otherwise clear. Good. So look, here's an example where our lowest priority group is hydrogen, but it's on the wedge bond. It's not on the dotted bond. And we would have the same problem, by the way, if the hydrogen were on an in-plane bond, on a straight line bond. There's a few ways to deal with this. One way involves using your mental capabilities of visualizing in 3 dimensions, being able to rotate objects in 3 dimensions in your head. And I will let you know that's a thing that's very unfair. We are all born with vastly differing abilities in that area. And I also will let you know that I was not one of the people who was born with particular talent in that area. I had to work very hard at it. Some people are just naturally gifted at visualizing and rotating things in their head in 3 dimensions. Lucky you if so. Career paths for such people. Surgeon obviously comes to mind. You know, if you can visualize structures like organs in your head, yeah, that'd be really great if you can be a surgeon. But hey, if not a surgeon, I would really want you to become something like an architect. Because boy, any house you built, I would not hesitate to live in. Any bridge you built, I would not hesitate to drive my car across. So it's a very useful skill, but we're all different in that area. So that's one possibility here. What we could do is simply flip the molecule over 180 degrees. That'll work. Now our oxygen will be over here. Our hydrogen will now be in back. And our CH2OH group will be over here. That's one possibility. Maybe it's the easiest. There's another thing you can do, which is to bear in mind that any time you switch any 2 groups, meaning you literally pull them off their bonds and switch them, you know, if you switch any two groups on a chiral carbon, you will flip R to S and S to R. 100% of the time, there are no exceptions. So that will work as well. What we can also do is switch the CH2OH group in the hydrogen and find out whether this is RS and observe the other one must be the opposite of whatever we just found. That works too. So those I think are the most common options. Turn the molecule until it is the way you want it to be, or I should show you one more example. Or like I said, switch any 2 groups you like, but be aware that you've also just switched R to S and S to R, and now you'll have to go back to answer the original question and flip it. And there's still a 4th way, but we'll get to that later. Before we tackle these, let's see what if, you know, the problem maker here had been evil. Let's say you'd gotten something like this. Let's say you'd been given this instead of what you had been given. So this is yet another way to deal with this. If you're, you could deal with this, let's say, by switching the H and the ethyl group. So if you're strategic about it, of course, if we switch the H and the ethyl group, then we get this structure, if I'm not wrong. Yes. See, right? If we switch the H and the ethyl group, well, this one is S, so that means this one must be R. Again, see if you can picture it in your mind. Switching those 2 groups. We put the H in the dotted bond and the ethyl group on this straight line bond. Isn't it the same as this? Everyone see what I mean? That's one way. That'll work. This one is S, so this one must be R. There is another way to deal with it. I'm just giving you all of the methods and tools here. You can use whichever you like. If there's ones that you don't understand well and you gravitate towards others, that's fine. One other thing we can do, let me kind of get rid of all that. Good. Another thing we can do is we say, well, we somehow need to rotate the molecule so the H goes here, the ethyl goes here, and the OH goes over here. That will also work. And so what I'm going to do is kind of grab this methyl group, and then I'm going to rotate the whole thing around that single bond. So I'm not really tumbling the whole molecule. I'm just rotating around a bond. And I think you can see the H will go back here, the ethyl group will come up here, and the OH over here. So what you'll get is the methyl group will stay in the same place. Wait a minute. OH over here. My hydrogen will now be back here, and my ethyl group will be on the wedge bond. So you see, I've just spun it, I guess, 120 degrees around that single bond. And so now what? Well, now our OH is priority 1, ethyl group is priority 2, methyl priority 3, hydrogen priority 4. I'm going to go 1 to 2, 2 to 3, 3 back to 1, ignoring the 4. That's a right turn, so it's R. Therefore, this one is also R, just as we predicted. So that's another way. And again, if you don't like doing it that way, you don't have to. There's multiple strategies here. I've given you the one with switching any two groups, which will always flip R to S and S to R, no exceptions. There's this one where you can rotate around a single bond. If maybe you can't do that because you've got a cyclic compound, you've still got options. You can maybe flip the whole molecule over like we did over here. And we'll assign this one next, I think. And there's just, let me see what are we doing for time. We have 10 minutes. I think that'll be just enough. To this day, I call this the Rochelle method because I had a student 21 years ago. So that's crazy. She's probably a parent and almost a grandparent by now, goodness. But be that as it may, I had a student who happened to be named Rochelle, I do not remember her last name, who swore by this method when she ran into situations like this, where especially when the H was on the wedge bond, like it is over here. This works only for those cases. But she swore that she did this. She would, let's say the molecule is on this plexiglass shield over here, facing towards you. What she would do is she would run behind the plexiglass shield where I am now, in her mind, look at it, and now the hydrogen that's pointing out towards you is pointing away from me. And she would then assign the things and turn her steering wheel and get it. You know, I'm honoring her to this day with the Rochelle method in dealing with those cases. It only works when the hydrogen's on a wedge bond. That's not going to work if the hydrogen's on a straight line bond in the plane. Then you have to do one of the other things. But she swore by that method, and it does work. So maybe that will inspire some of you. Okay, I think we've said enough on that. Let's assign some more of these stereochemistries. So let's see, what have we got here? Our chiral carbon is here. We can do it both ways. Let's see. So what's going to win? This carbon is double bond O. That counts as 2 single bonds to oxygen. So multiple bonds count as multiple single bonds to the same element. That's in the textbook and in the class notes. You don't have to worry about missing it. So we would count it that way if we needed to. Well, actually, I guess we do need to, don't we? So this is as if it were OH and OH twice. This carbon here also is a bond to oxygen, but only one. So I think the double bond O group is going to win. That's going to be priority 1. Then CH2OH has to be number 2. Since this carbon over here is just a CH2, there's no oxygens over there. So that's priority 3. And of course, our hydrogen is priority 4. So what are we going to do? We'll go from 1 to 2, 2 to 3, 3 back to 1, ignoring the 4. Looks like a right turn to me. That's going to be R, which means this one must be R, since it's the same thing. We just flipped it over. Had you chosen instead to pull off the CH2OH and pull off the hydrogen and switch them, so you get this molecule, that should still work. C double bond O is priority 1. Will hydrogen always be number 4? If there is a hydrogen, it will be number 4, but you may not have a hydrogen. We'll do an example like that in a moment too. Actually, this one over here is a terrible example. I want to do one with an H and a deuterium. But we'll do one like that. Actually, let's do this. I'm just sort of planning ahead. Okay, so we'll do an example like what you asked about in chat. What do you do if there's no H? We'll do one like that. I just set one up for the next one. Good, so that's number 1. CH2OH is number 2. The CH2 is number 3, and the hydrogen is priority 4. And the hydrogen's facing in back, so we're good. Well, now when I go from 1 to 2, ignoring the 4, 1 to 2, 2 to 3, and 3 back to 1, well, now that's a left turn. So this molecule is S, which means this one must be R, because we switched 2 groups. So that will work also. You can trust that method too. I'm just giving you options of what to do when you get something that's not set up in the most simple and straightforward way. And you know OWL especially will be OWL, right? So this will get you ready for that. And I've got a couple more examples over here, or at least this one. Maybe we'll do a deuterated one also if we've got a chance. And then I'll end with this whole situation over here. Well, actually, I might have said all I really need to say about that whole business. Good. So we'll really start in on this stuff next time. I just want to point out the 2 to the power n thing. Then if I have a few seconds to address this yet a little more, great. Any questions on this example? Does everyone see how I arrived at that answer? And I don't expect you to have it down perfectly right now. You have to practice, right? You're not born knowing this. Everyone knows that, goodness knows that's clear enough. All right, let's look at this guy then. Here I've been nice and set it up so that the lowest priority group is in back. Let's prove that the CH3 is the lowest priority group. I think you'll agree the bromine wins. That's like element number, I forget even what bromine is. I know chlorine is 17. Bromine is probably like 20 or 30 something. So bromine's going to win. Chlorine's going to be next. Chlorine is element 17, I think. Carbon is element 6. So now it's between the methyl group and the isopropyl group. The carbon in the isopropyl group has 2 methyl groups attached to it. This carbon is only hydrogens. So these carbons will beat those hydrogens. So I think you'll agree the isopropyl group is priority 3 and the methyl group is priority 4. So I was nice on this one. Why does it matter that the lowest group is in the back? Because you will get the wrong answer if it isn't. If it's not in the back, then if you go in to turn the steering wheel, there's a good chance you'll get the wrong answer. They need to have it that way so that it's standardized. Another way to answer that question is if you don't always put the lowest priority group in back, then you won't get a consistent answer all the time. If you did that, if you didn't put the lowest priority group in back all the time, we couldn't trust this method. It wouldn't give us one clear answer every single time. So, I mean, I don't want to sound like I'm pushing you off with, well, we do it that way because the rules say so, but that is the truth. And the reason the rules say that is to ensure that we get a consistent, trustworthy answer every single time. If we didn't always put it in back, we wouldn't have a trustworthy method. We'd get some answers that are sometimes right and sometimes wrong. So hopefully that answers that somewhat better. But yes, that's why it's part of the rules. So that is a thing that you'll need to know. You need to make sure that the lowest priority group is pointing in the back. It will often, if not usually, be hydrogen. It won't always be, and we've got an example like that over here. So I think I've established the different priorities here. Everyone okay with those? Good, well, let's see. I'm gonna ignore the 4. I'm gonna go from 1 to 2, shortest direction, 2 to 3, and 3 back to 1. Looks to me like that's a right turn, so I conclude that's R. And then you would name that, my goodness, there'd be, what is that, like 1, 2, 3. Oh, you want to call that, oh wait, 1, 2, 3, 4. How about we call that guy, maybe you want to go 1, 2, 3, 4, right? Because then we'll have a lower sum. What if we call that guy R, 2 chloro, 2 bromo, 3 methyl butane, something like that. That I think is maybe the best answer. Hi YouTube, everyone's going to be watching that part to see me do that again. Did I do that right? R, 2 chloro, 2 bromo, 2 chloro, right? You go alphabetically. R, 2 bromo, 2 chloro, 3 methyl butane. That's what I think that would be. That's the best I can come up with. Good. Let's also do one with isotopes, since someone asked about that. Just to save time, I'm going to put the lowest priority group in back. OH. Oh, except those are absolutely awful bond angles. Sorry, dreadful. Give myself an F for those bond angles. F in chat. And not the good kind. Yes, not the good kind of F. Bad kind of F. Okay, so everyone's putting F in chat. Great. Okay, so so you're making the in-person people jealous that they can't put F in chat. Okay, wait, I guess you could zoom in, but why do it? Okay, so I think we'll agree the oxygen's priority 1. That's going to beat all of these guys. Carbon's element 6. That's going to beat both hydrogen and deuterium, which are both element number 1. And then the deuterium beats the hydrogen, because deuterium is hydrogen 2, right? The deuterium nucleus has a proton and a neutron in it. The hydrogen nucleus is just a proton. So if you ever see D, that's what it means. It stands for deuterium, hydrogen 2. And hydrogen is, of course, 4. Well, shortest distance, 1 to 2, 2 to 3, 3 back to 1, ignoring the 4. Looks like a left turn to me. I'm going to say that's in the S configuration. Oh, crap, am I going to have to name that guy? Well, it's an alcohol, so we haven't learned to name alcohols yet. But looks to me like we've got a 3-carbon chain. What about S, 1 deuterio, 2 methyl, 1 propanol, something like that. I don't know if I bet the proverbial farm on that, but something like that. So that's how you deal with if you're given isotopes. You do the same thing if you had an oxygen 18 and an oxygen 16, other things being equal. Good, that leaves us with just 3 minutes. I think I've really already said about this situation. We're going to start here next time, start with drawing structures using this method. We'll learn about Fisher projections later. And again, there's always a few people who ask at this juncture, can we use Fisher projections? And I love it. I love the initiative, but no. Let's postpone that until next term. We'll draw structures using this method. And I will say it's important that the wedge bonds are horizontal and the dotted bonds and straight line bonds be vertical. That needs to always be the same. It always needs to be always like that or it'll be wrong. Good, so other than that, yeah, just attendance. Good, so we've got 2 minutes. I just want to point out this other rule here. That's going to come in handy next time. And as I said, there's little to no math in this class. I don't think you'll even need a calculator to do 2 to the power n type calculations. Though, if you need one, that's fine. But this is a nice thing to bear in mind, but we need to be clear on that. In a compound with n chiral carbons, there's a maximum possible total number of stereoisomers of 2 to the power n. That's the maximum. There could be fewer, but there won't be any more than that. So in a compound with n chiral carbons, you've got a maximum possible 2 to the n stereoisomers. That's going to include both enantiomers and diastereomers that we get to next time. So also read up on the definition of diastereomers. We're going to use that next time. Just a couple more comments on this. Let's look at the trivial case. What if there are no chiral carbons? Well, n equals 0, 2 to the power 0 is 1. So there's only one thing. There's no possibility for stereoisomers if there's no chiral carbons. If there's just one chiral carbon, 2 to the first power is obviously 2, and you will get the 2 enantiomers, just like over here. So that makes sense. If n is 2, 2 squared is 4. That means we've got a maximum possible of 4 stereoisomers. And next time we'll learn that this will generally be 2 different pairs of enantiomers, and any one of these 2 enantiomers with any one of these 2 enantiomers will be diastereomers, but we'll also learn there's a possibility of only 3 distinct stereoisomers. That will come next time. And that just goes up from there. If there's 3 chiral carbons, 2 cubed is 8, you've got a maximum possible of 8 different stereoisomers. Might be fewer, but the maximum possible is 8. And just to go from the sublime to the ridiculous, and I'll end with this, as I recall, cholesterol has 8 chiral carbons in it. And that's not rare at all for biological molecules. 2 to the 8th power is 256, if I'm doing it right. You can double check me. That means with that connectivity, there's 256 possible stereoisomers. Now, you know we get cholesterol in our diet, but we also biosynthesize probably most of it. At least that's what I've been told about people with cholesterol problems, which might include me, though we're working on it. Be that as it may, that means that of those 256 possibilities, only one is synthesized in living systems. I think that's just astonishing. And I mean, I will admit right up front, I am no biochemist. It's not an area of strength for me. But when I look at something like that, I just say, wow, that's absolutely amazing. And I am out of time, so we'll end here for now, and we'll pick up with diastereomers and this whole side of life with wedges and dots next time, and I'll bring my molecular models. Have a great day. We'll see you Wednesday.